Deep Talks. The talk tonight is with the Department of Materials and Metallurgical Engineering at South Dakota Mines, and we want to welcome them. My name is Mike Ray. I'm the Media Relations Manager here at this. Oh, thank you so much. I'll speak up. Is this better? Okay, thank you. My name is Mike Ray. I'm the Media Relations Manager at South Dakota Mines, and I want to welcome you all to Deep Talks this evening. The talk is going to be given tonight by Dr. Katrina Donovan, who is with the Department of Materials and Metallurgical Engineering right here at our own South Dakota Mines, which is a wonderful thing to celebrate. And I hope everyone had a chance to check out some of the art and the hands-on work that South Dakota Mines was so gracious to bring here. I want to thank Dr. Mike West, who's the department head of the department here, for bringing the great artwork as well, and all the students out there. If you did get to make a piece of art before, make sure to pick it up on the way out. It needs some time to cool because they put it in those hot ovens, and they'll be bringing it out. I do want to also give thanks to our sponsors, Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, Edward Jones, and Chuck and Jane Lichtenwallner. Without these folks, we wouldn't be able to have the wonderful beverages, food, and gathering here in Lead every month. And without further ado, I will turn it over to Dr. Donovan.
Thank you, Mike. I appreciate that. Can everyone hear me all right? Good. Okay, awesome. I also want to thank SURF for inviting us out here, and I'm really honored to be able to give this talk. I'm also honored to be the one giving this talk. I'm going to go through a lot of stuff, and I have a lot of acknowledgments because there's a lot of people that made this possible. A large part of this talk was done with Dr. John Keller, so he helped build part of it. So if you don't like the slides, he made those slides, okay? So without further ado, I'll get started. Here's the outline of the talk. I really wanted to motivate the background of the Black Hills, the minerals. We'll talk about some of the ways we use those minerals. We see these in everyday life and we might not even notice it. And then I'm going to go into a little bit of background of how we, with a new National Science Foundation grant, were able to integrate some of the beautiful things, the minerals in the Black Hills, into just the curriculum within our department, and then a little bit into the next steps and conclusions. So that'll be the outline for the talk. So let's start with the Black Hills minerals. When we think of the Black Hills, maybe one of the things that come to mind are, Deadwood, kind of close there. There's that nice HBO series of Deadwood. We might think Days of 76. These are things that would probably come to mind if we were to even talk to people outside of the Black Hills or even outside of South Dakota. But there's this association with gold, and there is a lot of interest in gold for sure, but there's so many other amazing minerals we get from the hills. On the right-hand side here, we actually have some wild clay. This is called Belfouche Shale. This is actually right from School of Mines campus. So this is one handful of it, but it's in a lot of western South Dakota. We have Belfouche and Pier shales, another type, but these shales are pretty common around the hills. So really what we're going to be motivating today is not just gold, but industrial minerals. And what do we mean when we say industrial minerals? What we mean is it's a mineral that's not used for its metal value, like we'd see for, iron, gold, but used for its intrinsic properties. So what we have here is some examples of those. So we have limestone, and we can see the limestone here. If you've driven through Rapid City, who here has been to Rapid City? Awesome. We've got some people. So if you've been through the western side of Rapid City, you'll actually see these limestone. There's the limestone in the northern part of the hills as well. Its composition is calcium carbonate. And so you can see right here that example, who here is written on a chalkboard? Oh, I was going to say, this is going to get really sad. This is going to be like my classroom. What's chalk? But calcium carbonate, you've also seen it in a chalkboard. It will look something like this. Light in color. Next we have muscovite or mica. This we'll see in the southern hills in Custer, and I'll talk about some of the companies locally that produce these. But mica you'll see, when I was little, before I knew about materials, we used to call this peel rock. Who here has seen this rock and you can peel parts of it? Yeah, we called it peel rock. It was very, very insightful for a 7-year-old. But lots of it around the hills. And then here's our formula. We got a little bit of alumina in there, potassium, silica. And so we see this in the southern hills. Montmorillonite, that's another one we see in Belfouche. Belfouche actually has a lot of it. It's pretty interesting. You might know it as kitty litter, which is on the left-hand side. It comes out of here and it's shipped on the rail cars going by School of Mines to Chicago, and it comes back to us as kitty litter. So there's that. The other thing that you might not know, but a lot of makeups, foundations, they actually have clay-based properties as well. So Bare Minerals is one of those companies. But here's an example of a clay mask. The other place, if you guys have played baseball, that you might see this, they use kitty litter to help it on a rainy day. When it gets really boggy, they'll put some down there as well. So a lot of places we see this. Kaolin, one of the places we've started is the Skyline Drive hogback. We found a sample there. There's quite a bit of, it's got a pretty red color along the skyline, but it's a nice deposit of clay. We also see, once again, it in makeup industry. But it's one of the big players when we're talking clay, so ceramic, dishware, those types of things. It plays a huge role in that. It also plays a very big role in glazing, so you can see some of the pieces up here on the right-hand side with the color. It's also used a lot in glazing. So there's kaolin. Quartz, it's nearly everywhere in the Black Hills. We'll see it in a ton of things. You notice we've got a lot of silica in these all the way around, but we see those everywhere. Here's an example of what it looks like. Another kind of disclaimer, you'll see silica as silica, flint, quartz, but this is what it looks like. Anybody recognize this? This is rose quartz. It's our state mineral. So it gets its color, that rose hue, from usually either manganese, titanium, or iron in those as well. So quartz, feldspar, also another big player here. And we see it in the Southern Hills. I'll talk about the companies that produce that. We actually are really, really well known worldwide for our feldspar, and I'll talk about why here in a little bit. But this is what that looks like. So now when you're on your next hike, you can look at all these rocks and know what they are. We're going to talk a little bit about wild clay. And this is a mix of a lot of these different things. Specifically, we'll talk a little bit about the shale deposit behind School of Mines. And shale can make things in terms of construction a little bit tricky for buildings and those types of things. So it's very important to know what you're working with. But that's what we'll talk about. It's a wild clay or a feral clay, or historically it'd just be the clay that somebody had in their region, and that's what they had to work with, right? Historically. So some of the companies that might work in this area, not might, but do. Pete Lean and Sons, they're located right in Rapid City. They started in 1944. They're a big producer of limestone. So right in Rapid City, we have those. Pacer, I talked about muscovite, that peel rock, right? Pacer's a big one. They have it in the Southern Hills right outside of Custer, and they've been operating since 1978. And they do a dry process for theirs. Montmorillonite, this one's actually a pretty interesting story. So in 1947 was when they started. They're still going strong. There's actually a research scientist in our department. He's from Belle Fourche. Who here has been to Belle Fourche? Yeah, we got some people. Better question maybe is, who graduated from Belle Fourche High School? Oh, we've got some. That's exciting. So it was really funny because I was talking with a colleague, and he was like, yeah, I know all about this. We have it everywhere. He goes, the bricks from my building were actually, part of it came out of this site. So it was pretty cool to see that happen. So the bricks that were made were right outside their back door, which is pretty cool. And then once again, you see Pacer here for their feldspar. One of the big things, we still have these chemical formulas. Sodium feldspar is a really common one, but one of the super special things about Pacer is their mine has a high potassium site, one of the highest for potassium, I think worldwide. Additionally, Pacer down in Custer, it's called Custer feldspar, but if you've ever had a Corel dishware or anything like that, that mineral, that feldspar is coming out of it. There's truckloads of it going to Corel in New York, and then coming back in terms of dishware. So this one is a huge player. The other big thing is they're the biggest feldspar producer within the U.S. So very big. And part of it, they have a huge mine, great site, but they also have that potassium, which is really important when you're working with these clay bodies. So limestone-based ceramics, this one we should really talk about because you can't look at a building and not see concrete or talk about cement. But for the minerals, feeds that include limestone, shale, clay, quartz, and iron ore, all of these minerals are readily available in the local hills, but that is what makes cement. So specifically, GCC is one of them in Rapid City that makes Portland cement, and that's shipped, once again, worldwide. But all of these just within our Black Hills, we can make all our own concrete, all our own cement, just from what we have here. So what we see here on the left-hand side, this is a site, this is GCC's site. And what you have is you have your kiln, which is this right here. It's used to react the minerals and form the Portland cement. So it comes down through and you have they're reacting, as you can see, at a really high temperature, 1300 to 1450, and they make what's called a clinker, and it's like a little round ball, and then they take that clinker and then they crush it up and they can use it for other things. This GCC is what it is now, but this was originally opened in 1923. It's also amazing if you ever get a site tour. I've been on a couple. They do a really cool job walking through all the different processes, but they actually still have some of those old buildings, but they've updated it when they purchased it in 2000. And this might not be within my price range, but trust me, $252 million for this was a steal. They've got a great operation going. And I said GCC, it's that company. But great operation going, and it still continues to this day, being one of the local industries that are primarily limestone, so we see a lot coming out there. Great company, like I said, if you've ever driven down like Omaha, near Chicago, it's the big plant there. So cement and concrete are probably some of the biggest ceramics we might think about, especially in everyday life from the concrete sidewalks we walk on. But really what I want to talk to you about today is clay-based ceramics. And so what we have for clay-based ceramics is we have these three different types here of mineral bodies. We've talked about quartz, right? That's our silica. We've talked about our clay. We can use that locally. And then we also have our feldspar. So what you do is you take these three different ones. Generally, we crush them down. But you can take them. Sometimes they're crushed enough if we get it from the earth in the right spot. But we take them, crush them, mix them, and then we add water. Who's played with mud? I have a lot in the last year, trust me. But then we add water, and then you form them. There's a multitude of forming processes. I don't have a 3D, oh I do. I have a 3D printed piece up here I will hand around actually as we're talking. So this was from our junior design. You guys will see it, but I'll hand it around so everybody can take a look at it. So that was a 3D printed piece. We're in this forming stage. We have to form our product. This one was pressed into a mold, so students did this. And that one is actually tuned, and no, I won't do twinkle twinkle on it, but it does work. And then this is a slip casted grubby up here, and I'll talk about the other in a little bit. But before we do any sort of drying or firing, we got to form it into the shape we would want. So lots of different forming processes we can have. Then it dries, and we really need to make sure these dry, because if they don't dry, as we heat them up, they'll actually explode because of the porous or any sort of holes it has that might be formed in it during the firing process. And there's really two places it can kind of blow up on us, and it's not a big blow up, it's a little boom in the kiln. But it can either be when we're adding water, we have too much water just within the forming system and that's coming off, or there's also water that's molecularly bound that comes off as well. So we form it, we dry it, and then we fire it. And that's what we see here. This is an example of porcelain. And we have a couple other glazed examples here. So this is an SEM of porcelain. We've got these bigger chunks here. That's our silica. We've got some molite in there. But when we're talking clay-based ceramics, I've covered the big ones. Adding water is that important point. And the kiln, it's showing plus 1,000 degrees Celsius. Depending on your mix or the chemistry of your minerals, you can go higher or lower. Porcelain is one that can go really quite high. I think we can take that one up to about 1,330 degrees Celsius, whereas the red clays, this is a red clay. I don't think we did the inside. You can see it's like a red-brown clay. Those are what's called a red earthenware. We want to sit closer to 1,000 degrees Celsius. And then you can see the decorative glaze. You also have to have your glaze matching the clay body you have, so you can't just paint anything on there. You need to make sure they match together. So, just a little bit of history about the production of clay-based ceramics, specifically in the Black Hills. So locally, and we're talking South Dakota Black Hills, we saw brick production was fairly common around 1900. And this was a piece, I think this was out of the Pier Gazette, or the Pier paper at this time, and it's quite old. We did quite a lot of digging for this, but they talked about using local minerals for making the bricks around here. Black Hills Clay Products is a really interesting one. It was operated from 1925, and it produced about 3,700 bricks per hour, which is pretty impressive for the time. Once again, using all those locals materials, and once again, right out of Belle Fourche, okay? So there really was the bricks made locally in the Belle Fourche area. This one's a fun one. This is Rushmore Pottery. So this was started by some of Gutzon Borglum's artists. They used a clay deposit near Hermosa. We're actually still looking for this clay deposit. From the road, you know, South Dakota, you don't want to cross fence lines. There's hunters and other people out there. But we're still looking for this. We've been driving and looking, but this is a really interesting one. We actually got this piece, but you can see this is one off of eBay that we purchased, and it says Rushmore Pottery on it in the Black Hills. And this one was super cool. Once again, that 1935 to 1942. I'm not going to go a lot into colors, but one thing to talk about colors is, you know, the colors we see in glass and in glazes, those are all metal based in some form, okay? Polymers are clothes. Any coloring you see there is usually polymeric, but to go to these high temperatures, you really need like metal oxide. So when you see a cool green like this, and if it has some history, it's probably uranium. So keep that in mind. They didn't know about it at the time. They just knew it gave them a cool green, but this might actually be a uranium piece. We don't have that, but we have this one back at School Mines. But this was out of Rushmore Pottery. Fun little fact about the permaclay. They called it permaclay because it was permanent clay, and they said you could throw it against the wall. I didn't bring them because there's always that one person in the crowd who really has the urge to throw it against the wall, just to prove it's not permanent. So, but that's where they got its name, permanent clay or permaclay. So, a little bit more recent, and one really cool thing I think is Sioux Pottery used to be just down the road from School Mines. It was located in Rapid, and it was a nice outlet for the Black Hills. They had some huge furnaces. They did actually close in 2021, but there is no current large-scale production clay in the Black Hills right now. So if you want a new market, guys, there it is. There isn't anyone at the moment. But the other cool thing is their clay bodies were 100% from the Black Hills. The glazes, not so much, but the clay bodies, they did. Some other local artisans and educators, just to shout out, that have been great collaborators for us. Pottery to Paint. They do different pottery. Prouty Pottery is also another great one in Rapid City. They have wheels and stuff there. And then the Doll Arts Center is another really good one that we've worked with in the past. In terms of just the closest vendor we have, we actually do a lot with Dakota Pottery in Sioux Falls. They've been amazing. They've supplied a lot of our commercial clay that we use, but also the wheels and any sort of processing. So just wanted to give a nod to all those businesses that really are in the hills and still doing work in this area. So I've talked about these minerals and talked about them. Let's just give a little bit more detail to why we care about their composition and what their role is. So limestone, what we see, it's used a lot in glaze. It's also called whiting. The calcium is going to be a big player here. It's going to be what we call a flux, and we'll talk about fluxes in terms of high temp materials in a minute here. Muscovite, it slows the glass vitrification, and you also see this a lot in wild clays. What is actually slowing the glass is this aluminum. It acts as a stiffener. It has a very, very high melt point. Potassium is a little bit more like calcium. It will help lower or flux your system, but it'll lower that temperature, but there's a lot of aluminum here, so this actually helps slow the vitrification process for us. Montmorillonite's great. It's a lubricator. It's a plasticizer. It's not desired in large amounts. Part of the reason is it'll take in a lot of water, and then if you're drying your piece, you don't want to spend a lot of time drying your piece. It'll take a really long time to dry. It can actually cause other problems, but a little bit in this case will go a long way. Kaolin, once again, clay, it's white. It's really desired for its color and properties. You see it a lot in both the clay body and then also a glaze. The other big thing, the white is a big component. If you do work in clays, you might be familiar with EPK, which is Edgar's Plastic Kaolin. It's in many formulations or recipes for both clays and glazes. Silica, that's our glass former. Anytime you look at a glaze, it's actually a glass coating on top of that. And so that comes from our silica. Feldspar, it's also used a lot in the glaze. It can be used in the body as well, but it's used as a flux. That comes from that sodium or calcium we can see. Wild clay, it might be, a Duke's mix of any of these. We really don't know unless we take it and do some characterization on it. So just switching gears a little bit, you have now a background of what is in our Black Hills. So what we did is we put in for an NSF grant. We were funded. We were really excited. The grant was for a glass studio, and we got it in, I think, the fall of 2021. Still, just economically, the U.S. was recovering from COVID, and we had put in orders for equipment that were like 2 years out. And we wrote this whole proposal around glass, and we're like, what do we do, right? What do we do? And that's really when, and it was Dr. Keller, he's like, well, we've got all these minerals in our backyard, what can we do? And so we shifted a little bit, and that's where the ceramics and a lot of my talk came in today, is we really shifted gears and took a focus more that way. I do want to dive just a little bit into what we were wanting with the NSF grant. So the big thing we wanted is we were looking to improve STEM education, and it's a program called IUSE at NSF. And so with that, we talked about the modification of labs, some co-curricular components being clubs. We have a new course now in glass, actually 2 new courses in glass and ceramic science. We also incorporated different components into our curriculum. So we have a metal clay lab now. We had a new class, and we had 3 weeks of glass blowing. So introducing some of these more artistic or creative ideas. We also have an artist in residence as part of this program, and she's gone through multiple classes with us and tried to find places where she can plug in and really help us with this. The big goals we want from this are creativity. So creativity, innovation, and I would argue creativity drives innovation, but that is an important part, right? If we're wanting to push materials and push the science forward, we need to be creative and think outside the box. Collegiality, there's a lot of teaming that happens here. Entrepreneurship, I'd argue, that comes right back into that creativity and innovation. The other big thing is student retention. We want our students to stay at School of Mines, want them to be happy and engaged in the program. So some of the places we did integrate that, just to quickly walk through, we have a first-year engineering program, so it's an introduction to metallurgical engineering. We redeveloped that class, and we have a multitude of hands-on modules. So some of the modules you have done out there, we've done something similar to that, where there's a technical component and then a hands-on to really reinforce that. And so 220, mineral processing, we've talked a lot about that. They actually, in that class now, they take wild clay and go all the way to a final product with that in a different stage. And then MET 231, we do metal clay pieces, which is actually what they're working on here. This is our artist in residence. She's leading this at a South Dakota STEM Ed event. MET 300 was a new class that was just offered this last spring. Did glass blowing in it, industry tour actually at a local mineral processing company. And then MET 352, really saved the best for last. That's really where we overhauled the class and integrated a lot of this mineral processing. And we've done that spring of 22 and 2023, and we'll be doing that again this spring. The big push is to integrate that art into the metallurgical engineering curriculum with the idea that with that art, we're gonna get creativity, we're gonna get out of the box thinking. Also, with working with our material, with different materials with your hands, you really learn how that material behaves. And it's a very translational skill. So some of the things we talk about in 352. 352 is our metallurgical engineering design class. When we talk about design, we usually want to talk about things like constraints and requirements. But where we started with them, I'm going to click through this really quickly, is we actually handed them 5 buckets. And we have what's called an XRD, and the XRD tells you what the different minerals are, right? So we gave them essentially 5 feral clays, and we said, make something with it. So they started, we told them an earth and ceramic pottery was the end product. We gave them an X-ray diffraction that gives us both atomic and molecular structure of the crystal. So it gave us the mineral we're looking at, but then it also broke it down atomically. So you know how much iron you have in it, silica, those types of things, so you can start formulating. They also had to handle the mineral processing, and there's, hunks they had in there. This is a 5-gallon bucket. So they had to get all the way down to a nice fine powder. So they had to work through crushing, grinding, particle sizing, all those important things. For example, here's some different types of clay bodies. So you can see a China clay, about how much aluminum you need, silica iron oxide, the calcium, magnesium, potash, soda. So you see the different types of clay, you're gonna have different amounts of them. One big thing to note is iron oxide, that gives us this nice red hue. You can see for a china clay, there isn't much. Over to a red clay, there's a lot more of that. So that's kind of where they started in terms of trying to figure out where they wanted to go in terms of their clay body. I did also just put the glaze up here. So here's the glaze formula. So we have whiting, which once again, that's that limestone, feldspar, kaolin, silica. Big thing to note is from a glaze, there's not a big step from a clay body to a glaze. It's modifying that chemistry so we can get the glaze to melt at a lower temperature. So you don't want your clay body turning into putty as well, you know, this big glob at the bottom. You want to mimic it with the glaze so it'll melt a little lower, but you still want that clay body to be sturdy. So they had to think about both clay and the coating or the glaze on top. So some of the final designs included materials, forming, and processing conditions. So they'd have to think things like weight percent, temperature, how high are we going to go in temperature to produce that final piece. There was also a competitive component we put in this for the final piece. We also discussed design difficulty. Some things are easier or harder. I'll pick on, this is my own team, but this is a coaster they made. And just the forming process of this might remind you of the cookies you make at home with your kids, right? There's other things they did, but if you roll this out and imprint on it, that might not be the most difficult design. But something like this, which was slip casted, might be a lot more complex, right? We've got Grubby's hat, we've got his nose, we've got his eyes. So, you know, complexity in terms of just the way it was formed is an important part. The coaster I showed you, which might not be amazing in terms of the way it was formed, it's 100% Black Hills everything, whereas the Grubby had commercial glaze put on it. So trade-offs there, but you know, those were some of the things we were assessing in terms of how well did they execute the piece, how tough was it, how creative were they, and creative can mean creative in the design, Grubby, or creative in the materials you use to get to a color or a process. So some of these have we've gone through. This is Grubby. This is Grubby before he was fired, so he's got this nice like reddish color. He was definitely had a lot of iron in it. This is a lot of Belfus shale actually, so it looks very black, but once you fire it, it turns into this nice red. And then that was him after glazing. This was a 3D printed ocarina. I did not know what an ocarina was until last spring. I got some smiles, so some people in here know what an ocarina was. I'm not musically inclined and I don't play Legends of Zelda, but the students really knew what this was. There was actually 2 of them last year. Processed 2 different ways, but I think one of those, you guys should have seen this, it had come around. One of the teams actually ended the semesters playing Twinkle Twinkle to us on their ocarina. So not only did they make it, form it, and glaze it, that one was 100%, they were able to tune theirs. So that was pretty cool. And then this one's coming around. We have another picture of this. This was actually a really interesting story I'll share with you guys in a little bit, but this is a mug that the students made. It was slip casted. And so when I say slip casted, back to that mud or that forming, they had really like a watery mud, we call it slurry, but watery mud, and they pour it into a mold, and then they wait till it has a shell and they pour it out. And so that's a mug the students made. So some other things we talk about in design is design methodology. How do you approach a problem? Another big part of design is this iterative part. Failing is part of design. You got to go back. I'd say it's part of engineering. You know, you got to go back when something doesn't quite work. So just quickly walking through this, we gave them the clay formulations. They had to determine their clay formulation. They got the minerals, but they had to then do some sort of processing. Their processing didn't work or get them to a particle size they needed, they'd have to go back. So here's just a couple different places that this team ended up having to go back and relook at things, but you can kind of see the flow as it down and over through here to finally being able to sell a product. And also determine is something plausible in terms of mass producing it. So like Grubby might be a little harder to mass produce than a coaster, right? So weighing all those types of thoughts and concepts into their area was important. These This team, their big thing, this was actually the coaster team, they really wanted to focus on the formulation. They were one of the few teams that had a purely white. This isn't glazed, this is a clear. They made a clear glaze, so they have a very white clay body, which is actually not always easy to do. They were trying to mimic a porcelain. So that was one thing they really wanted to do. The other thing, their glaze, it's a cobalt that's added, and that's what gives it the blue. So that was their two big things they really wanted to focus on. So I want to dive just a little bit deeper into the clay formulation. That way you guys are dangerous when you go home and decide in your backyard you're going to hit, dig up some feral clay. We kind of have these named based on where we found them. Tower Road is off of Tower Road in Rapid City. It's got some quartz. This was probably the best kaolinite we found in Rapid City, just a high amount of that. And then muscovite is in there. We have Fuson shale. This is a pretty white-looking one. Also another source of kaolin. That was the one the coaster came from. Custer's another big one. I talked about the Custer feldspar. Custer feldspar manages and operates the only actively mined source for high-quality potassium, or what we call potash, feldspar in the U.S. So it's about 85% and 15% mica quartz. And then Sturgis Road, they also were very interested in that because it had that calcium carbonate we talked about. Also want to say, I kind of based this off of one of the groups, but there were groups that also use Belfou shale, which is in our backyard. Core, you guys might be familiar with them. They're right here, in our backyard in Lead, right? They were really awesome, and they gave us a seam. They had a clay seam, and they were been really great to work with. But they gave us some of that, and some of the students worked with that clay body as well. So I want to talk a little bit more about the glaze part because we're kind of stepping through this. We have an idea of what a ceramic body looks like, but what do we want to do for a glaze? So here we have a phase diagram. So we have temperature on the left, and then we have alumina and silica on the bottom. As you can see, we're at 100% silica along this side, and that's really what I want to point out because silica is that glass former. It's what helps us both with glass and with glazes, and also just the clay body, ceramic bodies in general. But for the glaze, we want to optimize the ability to melt at a lower temperature because we want it to make this nice, smooth coating around our clay body. And really, if it's done right, it'll increase the strength of our clay body. So we're going to take advantage of what's called a eutectic point. So we have our liquid here, our liquid being one phase. It goes to two solid phases down here, a solid silica here, and then a molite phase. And so if you notice, this happens at about roughly 7 to 10%. So as you can see, it melts at about 1600. When we start adding other things to it as well, we can get it like calcium, potassium, or what are called fluxes. They help lower this so we can really use it for a glaze. So if we want to think in terms of clay versus glaze, that silica and that alumina, those give us a lot of clay body. This works really well for a clay body. This part looks really well for a clay body. Got quartz and mica, once again. Here though, that quartz is going to act as a glass former, and we use this actually a lot, the feldspar too. It works really well as a glass former in helping form that nice coating around it. A glaze is actually pretty similar to the glasses, and I'll talk about the chemistry of that here in a second. I want to talk now, we've talked through the clay, let's talk about the glazing part. And this is where we take what we have here and we start lowering that temperature. We're taking advantage of this eutectic point here. So we have alumina, titanium, calcium, potassium in this one. They all help us lower the temperature of our glaze. So that's something we would want to add to a glaze. Feldspar also helps with that. It's our flux. The color, as I said before, that'll actually come from your iron, titanium dioxide. Once again, here we see calcium flux. So big thing is if we want to have a glaze, we might add more of something that has fluxing and color in it, like feldspar, and we'd add more of that to our glaze body. So for a glaze formation, I showed this earlier. This is an example of 100% Black Hills glaze, but our glaze has whiting, that's calcium carbonate. We have our feldspar, our kaolin, our silica. And so this group, they used Fuson shale for a great majority of their clay body, but they also used it for their glaze as well. So you can see here, this is their glaze formula. They did add a blue cobalt oxide. I think if we didn't harness our students a little bit, they would go out in the Black Hills and dig. I told them no to going and getting this. There is cobalt in the Black Hills. We did buy commercial for this. It's the Morrison Chalcedony one, and it's kind of actually by in Wyoming a little bit, but there is some cobalt in that body there. So this group, they did 100% Black Hills. I have another group, and I'm gonna quickly emphasize this. They did a lot, and like I said, this group, they went out into the hills with a shovel. They roasted their iron ore. We told them there were other classes other than this they have to do as well. They were very engaged in this. They did a lot of roasting. They made their own copper ore. Sometimes I hesitate to ask where some of these came from, but they came up with some really creative stuff. So you can see a lot of these, you see there's cracking, there's problems. If we were back to that design loop, they had to go back and work on something because they had a couple different problems with theirs. You can see there's a lot of orange here, or you can hopefully see that undertone of that red clay. The problem is their glazes were needing to melt at a higher temperature than the clay body could go to. So they were having some issues. They had to modify the glaze to match the clay because this isn't something you're gonna wanna eat your cereal out of, right? It's got cracks, it's not even a nice coated surface. So big problem is they weren't going to high enough temperature for their glaze formulation, so they did make a modification. The big modification is borax. I haven't really talked about that, but borax was added, and that really helps lower the firing temperature. Borax is not isn't a flux, it's actually a glass former all on its own. Who has Pyrex at home, dishware? Or works in a lab and has, Pyrex, yeah. So borosilicate glass, it comes from that borax. Borax will be a glass former on its own. Big thing I hope you can see just from looking at this is it's got a nice shine to it, meaning it's got a nice coating, glassy coating, and then this was their final product. So other than the borax, they had 100% minerals from the Black Hills, but that borax did help make that glass former for them. Another area just wanting to talk about the forming part, there's the cut and stamp. There was one group that had essentially 3D printed their own cookie cutters. So we have a whole set of coasters back in my office, but there's, a lot of ways to be really creative with this outside of just the clay bodies. So leveraging technology, I've shown you guys a couple different things. We've talked about 3D printing. We had one group that 3D printed. This is a press molding process here. And then here's some of the clay pieces that were 3D printed by one of the ocarina groups. And they're using a 3D Potter printer as well. Couldn't not give a shout out, I guess, to just apps in general. Apps are really useful. YouTube's great, but they actually used an app to tune their ocarina. So one group had a tuned ocarina. Prototyping is another part. This was a group a couple years ago. I guess the first year they wanted shot glasses. Obviously an important part of a shot glass is to have the right volume in your shot glass, right? We definitely wouldn't want too little. We could probably argue the too much side, but we definitely don't want too little, right? So they did, a couple different iterations because when they did it, they were a little bit shy on the volume. One group, they got this is a polymer clay, and then they made a mold of it. They finally got to a version they liked where it was easy just to pull it out once the mold was made. So they would slip cast into that. So they had a proof of concept for that one. Scanning, this brings up a really interesting question. Oops, sorry. So this is Dr. West. He was introduced at the very beginning. He's a very good sport. If you've ever met him, had a conversation with him, he is very engaging. And so the students come in, and he's always willing to help the students. And they go, "Hey, Dr. West, can we scan your head?" He's like, "Sure, that sounds great." We had a conversation about how ethical is it to scan somebody's head and maybe not tell them what you're going to do with your head. And so he might have been a little surprised when the mug came out and it was literally his head. I will give the students props. I think this picture was taken like 2 minutes before final presentations. And he's got a glove on his hand because it was like out of the kiln, smile so we can get this in our final presentation. So super cool though. They were very creative. I think there's probably more mugs of his mug running around than he'd probably want because I saw some being made again. But they had a pretty good time just working through that. There's a couple different versions where they had to get, his neck right, his head to open to be a mug. So Yeah, fun conversation. So we're going to step just a little bit into kind of the next phase of the grant and the next things we were working on. These really might not seem aligned if you think about it. These glasses are transparent. These clay bodies are opaque, right? We can't see through them. So what is the difference, really? So I'm going to start just stepping us from ceramic bodies to glazes, and then the next step is from glazes to glass. So we've talked about a lot of these. I talk in terms of temperature. Do we have artists in here? Maybe? Nope. Okay. If you read any of the literature on clay bodies, we didn't always have a probe or a thermometer or something we could stick into something and say, oh, it's, 100 degrees Celsius or it's 1,000 degrees. We have wonderful tools today. Historically, what they had to do is they literally had to open up a furnace, their outdoor furnace or oven, and look in with their eyes to determine if their product was ready. So there's a lot of different cone systems, but that's how they did it. They took a cone and it would sit in a furnace, and then when it slumped, literally just a little slump, they knew their product was ready to come out. So there's an interesting cone system, but what I really wanted to talk about here is we've talked about a lot of these different parts, and I want you to see, we've talked about these in clay bodies. When we talk cones, we're actually talking a lot about glazing. The big thing to take from this is the glazing defines the temperature. So if we start at cone 10, it's a very high temperature. This is what porcelain's made at. We're actually not even low enough for some of the red earthen bodies, but I just want to work backwards here really quick. So you see we're at a 1-to-1 here, silica and alumina. The big thing to note is we see the potassium and the calcium don't change. Iron will act as a flux. These are our fluxes. As we go lower, these actually get lower for the aluminum and silica, right? Because we have 1 and 10 and we go much lower. So they actually had to measure the glass formers down because it was much easier to do that. So we measure the fluxes up. But big thing, once again, I like this because it shows what each component is doing. Our silica, it's that glass former. These are acting as a modifier or a flux. It's lowering that temperature. Iron is acting in that way as well. So really we use these cones, we being historically anybody that worked with clay or glazes, would use these cones as a measure of temperature. Even more recently, I'd say in the last 75 years, we've definitely done a lot more in terms of technology. We have a really nice kiln where we can do all sorts of awesome ramping with it. Historically, what they did with kilns is they would take cones, and the cones were composed of these different components, and then when it would slump, it would turn the kiln off. So it was really cool how they made those. So that's it. That cone system is used both for glazes and ceramic bodies. Here we've got glasses, and now we're taking that next step. So a soda lime glass and a clear glaze, we're going to see they have very similar chemistry. So if we look here at a clear glaze, it's cone 10. Said cone 10 is about 1,300 degrees Celsius, which would be roughly about 2,100 degrees Fahrenheit. But if we look here, we have whiting. Whiting has that calcium carbonate, feldspar, kaolin, and silica. I've talked about these a lot. If we look over, this is composition and characteristics of some common commercial glasses. I'm actually going to bring this one to attention. It's called what's called a soda lime glass. And if we look at it, I don't have all the percentages straight across, but if you see for silica, we're at 74%, but we start having a much higher amount of calcium and sodium here. We are at 16 and 5. And a soda lime glass is actually extremely similar to a glaze. They melt at a similar temperature. We can do modifications of the chemistry, but they're really, in terms of their chemistry, are quite similar. And I'm picking on the soda lime here because we do, introduce that, there it is, potassium in there, sodium in there. That helps lower that temperature, and we can really optimize this. So as you can see, soda lime, it's a nice low melting temperature, easily worked, also durable. It's used in a lot of different things. You'll see it from soda bottles to, I think they still use it in some windows as well. If you've ever been to a glass blowing studio, that's what they work with. The glass, if you guys did the slumping out there, it's a soda lime glass we actually had out there for that as well. So very similar. I did want to show this really quick. I think this is just super awesome science. So just bear with me for a second. But this is what a glaze looks like. As you take it up to cone 10, as I said, cone 10, about 1330, most of the melting actually happens in the last about 150. But we start here, which is cone 2, when it really starts melting is somewhere between here. It really begins to form a melt, and you can start seeing it starts looking gooey is one way to describe it, but you'll see the glass start dissolving the clay in the flint, these bigger pieces, that's your silica pieces. And so once it starts melting or fluxing, you'll see it gathers momentum as it goes. So carbonate is incorporated. We'll see the melt start taking over here, and then cones 6 through 8, which is about here-ish, for the glaze to start to melt, to begin to be completely melted. And so what happens when it starts melting is we actually end up with a completely amorphous, well, if it's done right, a metamorphous coating that we have. But it's really cool to see it step through. Whoops, apologies. One of the big things to think, though, is if the materials don't fit into the formula. So if you look at some glazes, some are nice and bright and shiny. Others have an almost dull appearance. It's actually different parts precipitating out. So it can be your metals precipitating out, and you'll actually get these really cool crystal patterns. But it's this last little bit that is pretty interesting. This was actually done on what's called a scanning electron microscope and a hot stage. So they just took some glaze and melted it through, but it's pretty cool. This work was done by Alfred University in New York. So for those of you that did have the opportunity to do some of the glass stuff, one of the big things we started discussing is glass, just viscosity, but also for glass blowing, it becomes really important. But for slumping, if any of you guys did the slumping, it's actually happening at about 700 degrees C, which is this working range. I did want to quickly walk through all of these. I'm going to stick with the soda lime glass curve, which is this yellow one. As you can see, it has a nice working range compared to, fused silica or this 96% silica glass. So we'll really kind of keep our eye on this. So the melting point, that corresponds to the temperature at which the viscosity is at 10 Pascal seconds. And it's, at this point, really from about here to here, we have what I would say is the consistency of honey. Like you've ever gotten honey and it's really, really, not a lot of viscous, and you got to roll it to get it onto your toast or your bread or whatever you're putting it on. That's about what the consistency is here. It's just at 2,000 degrees Fahrenheit. So, maybe a little bit different than the honey, right? It's a little warm. The crazy thing about this, though, as you work your way up this curve, we have our working point, which is right here, and you can still work with it. The melting point, that's a great, around here is a great time if you're blowing glass to be right around this temperature. Softening point is that point in which the viscosity is right around here. Maximum temperature at which the glass piece may be handled without causing significant dimensional alterations. So at this point, if you try working with it, it's like it almost starts flaking, really acting like glass. It's cooling. But you can also start causing problems with it, stresses, things that might cause it to crack later. The annealing point is really important. We actually, at this point, we want to put our piece into an annealer, and it'll just help hold it at a constant state or constant temperature. And when that's happening, you have any of your stresses being removed within that. So you can get stresses when you're working, and I'm going to click ahead just to show you. When you're working on a glass piece here, those tongs, it'll burn you, trust me, the end of these tongs, but they're cold relative to that glass, so you're putting stresses at that local spot. Any place you're touching the glass with a metal tongs or wooden blocks, any sort of thing, you're actually significantly cooling it and creating stress points there. So it's really important to anneal it and let those stresses be relieved, and that takes about 15 minutes. And then the last part is the strain point, and that's where fracture will occur before the onset of plastic deformation. So this is the curve. I think the biggest or coolest thing that has come out of glass working is a lot of people don't realize how fast you run up this. And when it's also, I work with students, and one of the things they say that's so crazy about this is you have a glass piece you're working in, and it's like you can take a metal piece and bang on it, and you can just hear that it's cold, but it's still so hot. It would burn you so terribly if you touched it, but it's amazing, for them to see how fast we run up this curve. The other cool thing about this curve that I like, I don't talk about color, but I'll show a picture here in a little bit. You can actually tell a lot about temperature of your material just based on the color. And so the students really got an idea of where they are on this curve just based on the color of the glass, the color of the punty they're using. So there's a lot of science, even though we're making some beautiful pieces, there's a lot of science behind that. And I can hand around some of these pieces. Some of these were actually made by Tony Gerlach. This is made by Dr. West, but I'll hand this around so you guys can see that. That's a paperweight. This was a blown piece that would have then been opened up. So something similar to like what she did here. So I've talked a lot about the curricular components. Another big part is co-curricular components. And actually what I'm showing here is what was done in class, but there's a lot of learning that happens outside of the classroom. We have quite a few clubs in our department, and just around campus too, but so much of that learning happens outside of the classroom. This was actually one of the students that was in MET 300, which is the new glass class we came up. This is Tony Gerlach. She owns Mind Blown Studios. She's also helping a lot with these efforts, but just a lot of different things she's helped us with over the last. So you can see some of the pieces actually here, but she's done a lot of really cool things. This is actually this piece before she opened it up. So she blew the bubble. Had done what's called a punty. You can see these metal rods. That's called a punty. And then she's opening it up here, and that's how she ended up with this piece. I'd hand it around, but it's got one sharp edge, and I don't want anybody to cut themselves, but feel free to come up and look at it afterwards. Another co-curricular part of this is there is also a U.S. Army grant where we did a lot of these similar types of curriculum. So summer internships, those are types of co-curricular components that have come out of this that have been beneficial. Just wanted to give a quick shout out. We've actually had a couple different collaborators with this grant. Tony Gerlach, a big one. Hopefully, if you guys are local, I mean really, really local, her studio is actually in Deadwood. So if you're in Deadwood, I got some head nods. Awesome. Yeah, you should go and watch her. She's done some really cool stuff. She's been a great support for us. Another artist that I'd like to give a shout out to, this is Professor Quentin Owens. He does a lot on the clay side. He's really, really good at 3D printing, actually, clay bodies. So he's done that. We actually had, at School of Mines, we have the Apex Gallery, which is an art place, but this was a really cool piece of work that was done by both Tony and Quentin, who've both worked with us in the past. So just wanted to say thank you to them. In conclusion, the MET 352 STEAM integration of the artistic mineral processing focus was very successful. The students comminuted, which when we say comminute, that means crush, grind, classify, different clay bodies to characterize the components of that. The students learned the scientific part, right? It wasn't all hands-on. There was a lot of different characterization, chemical formulation that went into their final products. We were also able to deliver a new course on mineral ceramics, talked about the rheology of clays. We talked about fluxes, glazes. That was also the course where they got to do some glass blowing as well, which was awesome. Big next steps for us are to include further engagement with the community. So doing events like this. I did want to give a shameless plug for a couple of other things with this program. So one of the other things we do is we offer a free workshop for teachers. And I did tell you guys I would talk about the color. Do you guys see how this looks red? And this looks, it's kind of hard to see. It looks more orange-red. I realize it's very subtle on here. She wasn't able to blow a bubble. We actually weren't hot enough to blow a bubble unless she was filled with more hot air than I am, which isn't the case. It was too cold for her to blow, and that viscosity, we were up too high on it. But it was a really cool picture. We were actually just doing it for picture purposes so she could send it to her husband. But just full disclosure, but it is a good talking point because it's like a very cherry red, and that's too cold, where this is like an orange color. We are also able to blow a bubble. So just 2 teachers that came and did this workshop last summer, once again offering it this summer. So we did a couple different things with this, from stained glass to glass blowing, but there's a science component in the morning, hands-on in the afternoon. If you have somebody that's interested, we also have a high school materials camp. Note, free is a big part of these. This is for high schoolers. They do a lot of different things here, everything from metal casting. We've done glass blowing. We've done, this is actually called torch work, where they have a glass rod and they're doing stuff. Science for Potters in Glass. This is the one that actually came out of this NSF grant, and we've got some very creative students. We also take them in. They get to see, this is different cracks. Actually, you can see the cracks in the glaze. If you zoom in, you can actually see the bubbles in the glaze as it was heating up and the bubbles were coming out. It's pretty cool to see that. different pieces they made, and then they also got to work at the glass furnace as well. So everything from color theory to, characterization to hands-on. So again, that's free. It's offered the 10th through the 13th. Science of Swords, that's a super cool one. It's actually offered June 24th through June 28th. We have a local blacksmith. He comes in. I'm sorry if I'm going too fast. I can slow down so people take pictures. Sorry. We have a local blacksmith come in, KJ Groven. He does a great job leading this. He has his undergraduate degree in mechanical engineering, so he does a great job of talking through both the engineering side of it, but also he's, as I said, a professional blacksmith, so he does a really good job with this group. I should also shout out, I don't actually have a picture of those students, but we also have a very competitive bladesmithing team. There's an international competition, and I think my favorite story about that is there was a group, they have swords from different parts of history, and so the fun part is they had a Viking sword, and there was a Nordic team, and the school mines beat the Nordic team. I'm not saying the Nordic team was bitter, but we did get a walk away with that, so it was pretty cool. Also, anybody watch Forged in Fire? Yeah, I've got some head nods. We actually have one of our students, this is Tyler, he was actually in a couple slides earlier. He, at like 18, was competitive and ended up on the show. It was pretty cool for us to see. But very, very involved, also involved in the blacksmithing team. And that really wraps up the talk. I do have a longer list than this. I did try and really get everyone in there, Tony, Quentin. If you want to see our website, for the record, I am not a professional website builder, so it's not the most beautiful, but it gives you a good idea of a lot of the things we've been doing, so go take a look at that. I don't think I've had the signups quite there yet, but you can look and see some of the things our students have been doing and just different outreach we've done. And I'll come back to this slide. I did want to give 2 references. If there was something you love from this is a great way if you do really want to go into your backyard. This book's awesome for finding different things. This was kind of our gold standard for the MET 352 because it covers both clay bodies and glazes. Linda's amazing. She is a materials scientist. She has her PhD there, but she really walks through the science of it, which is cool. And then here's our references. And I will end with, hopefully, a video. Maybe I will end with a video.
Of metal and glass to empower works of art. Students work with both professional artists and STEM professors to infuse their creations with metallurgical and materials engineering. Our projects are inspired by our industry partners to bring you to the cutting edge of science, engineering, and art. Come change the world with us. Check out this one-of-a-kind art and engineering program offered only at South Dakota Mines.
And that's the end. So thank you guys very much.
I think we might have a little time for questions if I'm not mistaken. Does anyone have a quick question or two? We're just right close to 7 o'clock for Dr. Donovan. Yeah.
How do you 3D print with clay? What are the logistics of that?
So the logistics of that are you have to find a nice balance between it being really runny, like I talked about, really just playing with mud and water, right? You don't want it so runny it doesn't hold its shape. So we talk about elasticity of our clay. We wouldn't want it slumping. So it's a mix between it being too runny to hold its shape, but not so like thick and viscous like a really hard block of clay to be able to print. So the things you're looking for is just, can we even get it to come through the nozzle? And obviously if we pour it, we can pour water through a nozzle, but it's not gonna hold its shape. So it's balancing the chemistry of the water with the clay body. The other thing you have to do is you have to be careful about your clay body because some clay bodies will really hold on to water. We're doing some actually 3D printing clay research, and we have pieces that are cracking all over the place because the clay doesn't like the amount of water we need to 3D print it. So trade-offs on the amount of water.
We're right at 7, but I
Sorry.
think we probably have time for just one more quick question. If you can make it fast, is that okay?
You learn this as an instructor. If you just go to time, nobody has time for questions.
Okay, I'll be quick, but I think it's really cool just how, how art is going into this, and then you have chemistry and all that. And this is the first time I kind of been to one of these events, and so seeing how many programs that you have is really amazing. And I'm just out of curiosity, as you were like growing up, was there anything that inspired you to get to where
I would say I have always had an interest in science and engineering. So that was kind of my journey. I would say was I worked for a gentleman who had a lot of art and just really cool to see. I also, how can we modify the chemistry to get a specific color to side that drives me, but it's cool to see how somebody else can use the local glazes this summer based off of some things, and a failed one. They're like, I love it, I want it, can you do it for me? And I'm like, using some of my failed glazes this summer. So, but it is cool to see the students that definitely have that art passion. You know, they're in the program, which is awesome. That's
great. Thank you. Next Deep Talks is on December 7th. We'll have a little physics discussion about that. So put December 7th. Again, our sponsors, Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, Edward Jones, and thanks to them, we're able to have these wonderful events here.